Bismillah ar-Rahman ar-Rahim. So let's look at this section or this lecture. Diffusion and dispersion. This is part of water quality modeling class. Okay, so of course we're gonna be discussing in this class advection versus diffusion. Of course, you're gonna be talking about Fick's law and other transport mechanism. Of course, you have to come to class by reading the lecture number 8 from Steve Chopra. We'll have some assignment coming up in class, and there is no announcement. The learning objective of this class is to calculate diffusive flow, dispersion coefficient, dispersion flux, and we can formulate and solve system of CSTR that include diffusive fluxes, and then can define advection, diffusion, dispersion, and articulate the differences between these transport mechanisms. Let's try to show some definitions. What is diffusion? Whether the diffusion is molecular diffusion, which is like due to molecular motion within the molecule of the pollutant, or turbulent diffusion, which is like due to turbulent eddies inside the water. Of course, we have to lump these into one lump together all the way once we talk about diffusion. Dispersion, on the other hand, it's occurred due to the velocity gradients, movement with the flow. Dispersions and diffusion reduce concentration for sure. So the concentration gradients of the pollutant can be reduced with the ability of diffusion and dispersion phenomena. Mass move from higher concentration to a lower concentration. Let's look at the mass transfer by random motion, which is diffusion. We know the movement of mass due to random water motion or mixing is called diffusion. That's what I just mentioned the last slide. To model this, let's consider a tank separated by two well-mixed sides. This is one side, and this is another side. And these two tanks are connected. You can see that side 1 has a concentration C1, side 2 has a concentration C2, and of course side 1 has a volume and side 2 has a volume. And the diffusive flow coefficient, we could call it D prime. The pollutant will diffuse from tank number 1 to tank number 2, and we could call this the diffusive flow coefficient. And also the pollutant can diffuse from tank number 2 to tank number 1. Okay? So if you want to do mass balance only in this side, you can see that V1, volume 1, dC1 over dt, the change of concentration with time, is the diffusivity constant, which is the diffusive flow coefficient, times C2 minus C1. C2, what is C2? C2 is the concentration of the pollutant in the tank number 2 minus the concentration of the pollutant in tank number 1. If C2 is higher than C1, then it's going to be positive, so the mass will flow from side 2 to side 1. If C1 is higher than C2, then it's going to be negative, so mass move from side 1 to side 2. So it's all depend on which concentration is higher. So if this is this way higher, then this term going to be positive. So it's going to move from tank 2 to tank 1. If this is true, then it's going to move the opposite from side 1 to side 2 because concentration 1 is higher than concentration 2. Diffusion can act to reduce concentration differences, and mass always move from a higher concentration to a lower concentration gradient. For example, if you have all these flow in, flow out, there's the loading. This is for the main lake, number 1. And let's look at the bay. There's a loading in the bay, and there's a flow in. And you can see that there is flow from the bay to the lake, and there is diffusion movement between the bay and the main, back and forth. So this is what I mean by diffusion. Okay? So if you want to do mass balance for the main lake and the bay, V1 dC1 dt is equal load 1, which is the load on this lake, minus Q1 C1, of course, minus the flow rate if you have flow rate coming out of the lake, minus anything happening inside the lake reaction, plus Q2, C2 coming up from here, from the bay, plus any diffusivity, E prime C2 minus C1. Same thing if you want to apply the mass balance for the bay, V2 dC2 over dt is the load in the bay, minus Q2 C2 minus any reaction, plus the diffusivity C1 minus C2. And of course, has to move from C1 to C2 if you want to have it positive. So it's depending on the concentration gradient. These are the symbols. V1, V2 is the volume, C1, C2 is the concentration, W1, W2 is the external loading, Q1, Q2 is flow rate out of the main lake and the bay, K1 and K2 is the first order loss, settling, sometimes decay, sometimes volatilization, depending on, and E prime is the diffusive exchange flow between the two water bodies. Let's assume that we have two CSTR and pollutants are moving. There is a diffusion of pollutant from CSTR1 to CSTR2 and from CSTR2 to CSTR1. So let's look for the compartment 1. V1 dC1 dt, usual terms, flow rates, loading, reaction, volatilization, and settling, plus diffusivity, C2 minus C1. If you want to do for compartment number 2, V2 dC2 over dt, it's usual terms, plus A prime, C1 minus C2. A prime is the diffusion flow. Unit is L cube per time. E, which is the diffusion coefficient, it's unit of L square time over time. So if you want to do the relationship between A prime and A, which is diffusive flow, and A is the E, I mean the diffusion coefficient. The relationship between A prime and A prime is equal, E prime is equal E times the area, and I'll show you in the next example what is this area that we're talking about, the area of mixing between the bay and the lake, or between the bay and the ocean, okay? And E prime is equal, if you take this one as a common factor, it's E over L. E over L, it's the velocity. Okay, so E over L is the velocity. Okay, and that is VE. VE times the area of mixing, area C. Now, let's look at the rest of the equation. The VE, which is the velocity of the movement of the pollutant, is E prime over AC, and that is equal D prime diffusivity, another parameter called D prime over AC, or we could call it D over length, length of mixing, okay, length of mixing. So right now we could deal with that E prime has the unit L cube over T, and E is L square over T. And if you want to make sure that these things are homogeneous, you could multiply E prime, and that is, which is L square over T, times the area, L square, divided by the length, L. Then you can see that L cube over T, because one L will cancel with one L, so you're going to have L cube over T, and that is, the dimension right now is consistent, and there are many equivalent ways to express this relationship. We'll choose whatever is most convenient for the system model. Okay, so now we'll give you an example. Let's estimate, but before we start the example, let's estimate diffusion. We have a bay and lake, and now we will have an example in the class that we will do the diffusion between the ocean and the bay, Quake Bay. We'll mention that in class, which is similarly the same thing. The Bay-Lake model can be used to estimate the bulk diffusion coefficient for cases where there's a gradient of conservative substances. Why we choose conservative substance? Because K is 0. There is no volatilization, there is no settling, there is no decay whatsoever. Because we want to check here, we want to put this conservative substance and we want to see the diffusivity constant, or the diffusivity between the bay and the lake. If you want to do a mass balance, V2 ds2 over dt, which is the concentration in the main lake over time, it's loading W2 minus Q2 S2 plus the diffusivity constant S1 minus S2. Okay, so if you're gonna make this one equal to 0 at steady state, you'll end up with diffusivity exchange flow. It's loading 2 minus Q2 S2 over S2 minus S1. Let's look at an example. We want to estimate the diffusion coefficient E for the Saginaw Bay and Lake Huron system. Let's look at Saginaw Bay. Saginaw Bay is like this. It's like Kuwait Bay. And this is the mixing length, and this is the bay. This is 2, and this is the lake. This is Lake Huron. Okay. And here is the diffusivity between the lake, just make it lake, and this is the bay. Settling velocity is 16 meters per hour. Now we don't have a conservative, now we have 16 meters per year, sorry. Mixing length, the mixing length from here to here is 10 kilometers. Mixing area, if you look from this side, this is the mixing area. The mixing area is 0.17 10 to the 6 meters square. He has the bay, and this is from the book. You have the volume, 8 10 to the 9 meter cube. You have depth, you have surface area, you have outflow, you have chloride concentration, you have chloride loading, and you have phosphorus loading, and you have volume, depth, surface area for the lake, and everything else is listed in this table. Let's find out, since we will be dealing with, here we want to find out the diffusion coefficient for example, chloride, which is chloride is a conservative compound. So we should find out E prime. E prime from the previous slide is W2 minus Q2 S2 over S2 minus S1. And W2, the loading, it's here, loading of the chloride, it's 0.353 10 to the 12, 0.353 10 to the 12, minus Q2 S2, this is 7 10 to the 9, and the chloride concentration is 15.2. So we have this times this divided by S2, 15.2 divided by S1. S1, the chloride concentration is 5.4 gram per meter cube. So this would give you E prime 25.2, 10 to the 9. Look at this, meter cubic per year. You can see the differences right now. That the diffusive exchange rate, E prime, is much larger than the bay outflow. Remember, the bay outflow is 7 10 to the 9. Let's just go back. It is 7. This is the bay outflow going from the bay to the toward the lake. 7 10 to the 9. Look how much diffusive you have. 25.2 10 to the 9. Remember, 7 10 to the 9. This is the amount of water physically flowing out of the bay into the lake. Okay? This is very important because the relative importance of diffusion, mixing, compared to actual water flow, advection. So actual water flow is advection, and diffusion or mixing is, the diffusion here is more important than the actual water flow advection. The A prime, which represent the effective volume of water that is being mixed back and forth between the bay and the lake. Remember the bay? Back and forth between the bay and the lake. Of course, the mixing back and forth between the bay and the lake, because it's because turbulent, diffusion, and circulation. All of this is happening, and that is much more important than the actual water flow. Let's continue. Of course, the area of the mixing is given 0.17 10 to the 6, and the length of mixing 10 kilometers. You have to make it 10 times 1,000 meter. And here you could find out the mass transfer velocity. This is the mass transfer velocity from the bay to the lake, and from the lake to the bay. It's E prime over the area of the mixing. This is the area of the mixing by looking from this side, and that would give you 1.48 10 to the 5 meter per year. That's huge amount of mass transfer velocity from lake to bay and from bay to lake. And later on, we're going to find out the diffusion coefficient, which is VD times the length of mixing, which is 10 kilometers or 10,000 meter, and that will give you 1.48 10 to the 9 meter square per year. This E, the diffusion coefficient, is the effective diffusion, which is can be called also dispersion coefficient. And this E represents how pollutant can spread out over distance, over a horizontal distance in this case. There's other transport mechanism like turbulent diffusion, which is mixing due to turbulence eddies, and much stronger than molecular diffusion in natural water. And also, if you want to talk about dispersion, which is mixing due to velocity gradient in the flow, which can cause mass to spread from high concentration to low concentration. Diffusion is microscopic mixing, very slow. Dispersion is mixing caused because of flow patterns, much faster in natural system. Of course, there's a lot of examples, like in rivers, water in the center flows faster than water near the banks because of frictions, and pollutant slug gets into stretched and smeared along the river. This is what we call it dispersion, and at the same time, molecules continue to randomly spread, and that is diffusion. If you want to compare both, like diffusion, it's caused by random molecular motion. It happens in still water. It can still happen in still water and moves mass from high to low concentration. Dispersion, on the other hand, velocity differences in flowing water, there's shear and there's mixing, and occurs in moving water system only, rivers, estuaries, and bays, and can spread pollutant because different layers move at different speeds. Let's look at the last example, bay to ocean diffusion problem. Let's look at the bay area is 10 to the 6 meter square. And that is, if you want to look at this example, let me draw it for you. And this is, let's say that we have the bay, and we are looking sideways. And this is the, let's see, the sea surface. This is the bay. And this is the ocean. And you have Ministry of Public Work dumping, let's say, stormwater runoff into the bay. The area of the bay, let's say that, let's see, this is the line of mixing. The area of the bay is 10 to the 6 meter square. This is the mixing area between the bay and the ocean, mixing area. And by the way, we are looking sideways from the side. And mixing, exchange, cross-section. And this is the cross-sectional mixing and exchange. It's from looking from this side, okay? This is the area, 2,000 square meter. Before you discharge, and before Ministry of Public Works discharge any pollutant using the stormwater runoff, the concentration in the bay, concentration in the ocean is zero, because ocean always act as an infinite sink. It will take all the pollutant and dilute it so quick. Pollutant is conservative. Let's assume it's conservative and no K, no settling, no volatilization, no decay. So bay flow is QB 0, which is very small and can be neglected. And let's assume that VD is 4,000 meter per day, which is diffusion mass transfer coefficient. We want to find out loading to the bay and assume that concentration of the pollutant in the bay, of this conservative pollutant, is 10 milligram per liter. Okay, let's look at the diffusion relationship. Remember, E prime is equal E, the area of mixing, over the length of that mixing area. And if you divide E over L, and that is VD times the area of mixing. And if you want to do bay mass balance, volume dCB over dt is equal loading of the bay plus E prime C ocean minus CB. And we said that the ocean is really big and huge and everything, and will be a sink. So C naught is equal to 0, and then, of course, at steady state, this is going to be equal to 0. So loading of the bay is equal E prime CB. And E prime, as we mentioned, it's VD times AC. So VD times AC times the concentration CB. So this is the loading of the bay. And that will give you, since we have AC, we have VD, we have CB, we could find WP 2,000, this is meter square, times 4,000 meter per day, times 10 milligram per milligram per liter, or which is equivalent. This has the same units, or gram per meter cube. You can see meter cube, that's gram per day. So this is gram per day. It's going to be 8, 10 to the 7 gram per day. If you want to do gram, kilogram, so 1 kilogram is 1,000. That's going to be 8, 10 to the 4 kilogram per day, which means 80 tons. So loading of that conservative pollutant, it's 80 ton per day. Okay? So by knowing how much is the concentration in the bay, we could know how much the stormwater runoff is loading into the bay itself. Thank you.